In the previous video, we discussed the concept of hypothesis testing and also type 1 error, alphas, rejection, or not to reject, p-values, all of that. In this video, our focus is on type 2. We are also going to solve a complete problem and discuss relationship between type 1 and type 2 errors, and also one-tail versus two-tail tests. So let's comprehend what these two are first of all. So type 1 error is when you reject something which is good. Type 2 error when you don't reject something which should be rejected, something which is bad. So let's do a quick example to save some time. In this situation, for instance, null hypothesis is defendant is innocent, alternate guilty. If you reject a true null, which means if you send this person to prison when actually he or she is innocent, that's type 1 error. Something was good, you said it was bad. Type 2 will be defendant actually is guilty. That means null is wrong, null is false, but you didn't reject it. So you sent the person home free. That's type 2 error. So with that in mind, let's go to our real thing, which is solving a problem. Now this one is a very special problem I created for this purpose. So what it is right now here is that a company called Pioneer Surplus wants to purchase some B-level parts from Nico. Now Nico does not know how many are defective, but they believe based on previous experience, 14% or less are defective. It's a huge lot, nobody has time to check it and cost a lot of money to check. So that's what the belief is. Now Pioneer loves this deal. They're getting a very good deal, good price. But there are two problems with this deal. One is, what if suppose when they pick a sample of parts to check, the sample shows a lot more defective than actually there are. For instance, actually the only, let's say 13% defective, but the sample shows 35% defective. Well, then you're going to say it's a bad lot, don't do it. Type 1 error. Reject a true null. Reject a good lot. Type 1 error. At the same time, it's very possible that the lot is really bad. Null is false. 25% bad. Should not be bought. But the sample shows only 12% defective. Well, then you think, let's buy it. Well, then you realize you've made a very bad deal. So you lose money. So the statistician Rashmi has this idea of take a sample of 200 parts from this one and reject the lot if 18% or more are bad. Now remember, our target is 14%, but we are saying 18% or more bad are still okay. Because we know in a sampling, sometimes 15 will show, sometimes 16 will show bad. So up to 18%, she thinks it's okay. So this way, they increase the probability of accepting the lot and decreasing the probability of rejecting a good lot. Now the cost accounting department has given this table of the profit versus defective. If 10% defective, they make $45,000. Well, it's very possible that in this lot, only 10% are defective. Nobody knows really. So they may get lucky here. 11%, 12%, 13%, 14%. This is what target is, 30,445. That's what everything is based on. Because that's what they claim, 14% defective. As the defective percentage goes up, profits start to decline. And here you get red numbers. Don't want this lot. If you by any chance get this lot, this defective, you say, okay, well, I didn't make $30,000, at least I made some money. But here, money coming from your pocket. So right now, without much explanation, type 2 error is probability of accepting this lot. That's type 2 error. That's it. How do we get it? That's our job to figure out. Here are some details. 14% defective. That's what the claim is. I could have put less than or equal to 14 also. And alternate is more than 14% defective. Sample size is 200. Cutoff point is 18%. If you get 200 parts, 36 parts or more defective, that means reject. Less than 36, take it. Now we're going to solve the problem. So here again the details we just discussed. And then from statistics, you can use this formula to find the standard error of sample proportion. Sigma p hat equal to this one, which is that. Now if you've done sampling distribution, then you should know all those things. That's coming from the sampling distribution. Now it's called standard error of sample proportion. Now that we have a mean and a standard deviation, we can have a normal distribution. Now something special about this problem, which is I started by saying cutoff point is 0.18, 18%. Normally we do not do that. Normally we go type 1 error is 5%, alpha is 5%. The reason I'm doing this way is that when I said type 1 error is 5%, students get confused. They cannot, it's hard to really connect type 1 error, etc., etc., etc. But cutoff 18% is very intuitive. Very simple. I take a sample of 200, 18% more are defective, take it back. Less than that, we accept it. That's very intuitive. But indirectly, if I find the probability of 18% or more, it's 5%. So I can very well say my type 1 error is 5%, but I calculated it in a reverse way, just to make it more interesting, more understanding. So in this picture, this is what it is. If the mean is 0.14, that means proportion is 0.14. There is a 5% probability that in a sample of 200, 18% or more will be defective, which means it is possible that these numbers does not mean that this is wrong. But we say anything more than 18%, we are going to reject it. So indirectly, we're taking 5% chance of being wrong, because 5% probability that if mean is true, if null is right, you may end up in this area. But we said we don't want it. And here I have the pioneer's policy. This is very critical. If the sample defective rate is less than 18%, accept the lot. That means if you belong here, accept it. Belong there, reject it. So far so good. This is all from type 1 error from our first video. This is all we have done before. Now comes the second part of type 2 error. And what we're looking for is the probability of accepting a lot which is this bad. That's we don't want. This is still is okay. We don't want this. How do we figure that out? Let's think about it. Suppose it's this bad. Suppose this is 0.22. Okay, that's what we're guessing. The warehouse defective rate is 22%. So actual is 0.22, which means null is false, got to be rejected. Which means if you accept the lot which is this defective, we commit a type 2 error. Why would we accept it? That's the question. Well, here's our policy. If the sample defective rate is less than 18%, accept the lot. So what is the probability that a lot this defective will generate a sample of 200 in which less than 18% will be defective? And that's type 2 error. So here is our second normal distribution. Here are numbers. Mean is 0.22 because this is 22% defective. What's the probability we'll get 18% or less defective? That's it. Let's find it. There we are. We use normal distribution again here. So 0.188, 0.18 is x, that's this one. 0.22 is the mean. This is the standard deviation and cumulative, just like we did here. We did 1 minus because you're looking for this side. Excel always gives you results from this side that way. So here we didn't have to do 1 minus. Here we had to do 1 minus. So 0.053, type 2 error. Now, what's the whole thing is in English? That basically means, first of all, in two ways. First of all, it means if the mean is 0.22, there is 5.3% probability that the sample will show 18% or less defective, when actual defective are 22%. We can also say that this way, if the actual parts are 22% defective, there's a 5.3% probability that we are going to accept the lot because of this rule. Sample defective rate is 18% or less, accept the lot. Well, that's 18% or less, accept the lot. So, type 2 error probability now is 0.053, 5.3%. And this is what type 2 is all about. Once you have the cutoff, once you have to make a decision rule, when to accept and not to accept. So that comes from here, type 1 error. That's your cutoff. Now from this cutoff, you say, what if 22%? What if 21%? What happens then? Or 20%? Or 19%? These all are type 2 errors, by the way. If 21% defective, if the parts are 21% defective, what's the likelihood we are going to accept it? Type 2 error. If they're 20% defective, 19% defective. So these are all type 2 errors. And guess what? We're going to work on it right there. Once again, use normal distribution. So at 21% defective, our type 2 error is 11.35%. That's the probability of acceptance, which means you're accepting a lot, which is this defective. If it's 20% defective, it's 21.17%. 19%, this much. 18%, this much. Look at 14%. 95% acceptance, which means 5% rejection. So at 18%, 95% we're going to accept it, 5% we reject it. And that 5% is called type 1 error. Rejecting a good lot. There. How about at 13% defective? At 13% defective, our acceptance probability is 98%. But rejection is 2%. At 12%, so basically if it's a less than about 13% or so, we are going to accept for sure. It's pretty much very high probability. At 14%, 5% rejection, 95% acceptance. So now the management has all the resources. There's about 5.3% chance that they're going to lose money, about this much money. Now they can decide, take it or leave it. And I would say just take it because 5% chance is very small and you only lose $2,000. Not that you're losing a shirt, right? But whatever. But our job is done. So let's move on to the other things that we are going to discuss now. Type 1 versus type 2 relationship. Here I've drawn the pictures in this way. So this 18%, 18%. 5%, 5.3%. What happens if the line moves this way? Line moves this way, this becomes less and less and less. What happens here? This becomes more and more and more. So it means as type 1 becomes less, type 2 goes more. As type 1 becomes more, type 2 becomes less. Your choice, what you want. Sometimes we want to minimize this, sometimes we want to minimize that. But the reverse effect is minimize that, that grows up. Minimize that, that goes up. There we are. Okay. So here I've calculated the probabilities of alpha at different levels. 1%, 2%, 3%, all the way to 10%. So if it's 1%, cutoff is 0.197, which means that 0.18 comes down to somewhere here, 0.197. So type 1 error is only 1%. Type 2 jumped from 5% to 17.51%. If it's 2%, 3%, etc. At 5%, its cutoff is 0.18, what we had it, and 5.3%. Now, if alpha becomes more like 6, 7, 8, 9, 10%, type 1 becomes less and less and less. Once again, you decide where you want to be. It's your call. There's no right or wrong here. Now, which of the two errors are more important? 1 or 2? Well, there's no such thing. Innocent, but jury sent her to the prison. Type 1 error. Guilty, but the jury let her go free. Type 2 error. In this case, in most countries, we minimize type 1 error. Because you don't want to send an innocent person behind the bars. What happens then is this becomes big. Guilties go all the time. The only thing is, guilties hopefully will get caught again, but at least innocent person will not rot behind, in the prison. Minimize type 1 error. In this situation, patient is healthy by default. Patient is sick. So the patient was healthy, but doctor sent him for MRI and lab work. What's the meaning of that? Well, the patient was fine. Null is true, but the doctor rejected it. That means doctor said patient is sick. Because he is sick, go get some blood work done, get some MRI done, get some X-ray done. Type 1 error. Type 2 will be the patient was really sick, but the doctor said, go home. Everything's fine. You are perfectly fine. That's type 2 error. In this case, what we will do? We'll minimize type 2 error typically. Which means what? Which means type 1 goes up. Which means lots of people who are perfectly fine, nothing wrong with them, they simply have a stomach pain or something's going on there while they go through unnecessary MRIs, lab work, blood work, X-rays, and who knows what. Unnecessary tests happen a lot in medical world because you want to minimize type 2 error. Lots of guilties go free in real life because you want to minimize type 1 error. Minimize this, that goes up. Minimize this, that goes up. You decide what you want to do. In our last slide here, we have one tail versus two tail tests. Let's suppose alpha is 6%. If it's 6%, we have a one tail left side here, left or right, doesn't matter. 6% is our, so you fall here, you get rejected, here don't reject it. So X bar, the sample mean falls here, reject the null, don't reject the null. Here's the two tail tests. This is split into two parts, 3% and 3%. If X bar falls here, reject, here, reject. Falls here, don't reject. False here, don't reject. Correct? It makes sense. Now suppose our X bar happens to be here. And suppose this is 4%. That means this is 4%. Right there. That's what we call p-value. P-value is what? If the mean is this much, what's probability of finding X bar this or more? That's p-value. 4%. If it's a 4%, then don't reject the null because look at the picture. No rejection, rejection, rejection. Don't reject it. Correct? That's what picture says. Now we have our alpha at 6%, p-value is 4%. And what did we learn so far? Reject the null if p-value is less than alpha. But it is 6% versus 4%. So which of the two is right? Don't reject the null or reject the null. That's the dilemma we have. So what's happening here is that we split alpha into two parts. 3%, 3%. We are comparing the 4% to half of this. And that's not fair. So what we do is we multiply that probability by 2 and get 8%. So which means the 4% is treated as 8%. 4% and 4%. This is simply to make sure that we are consistent. Now we can say alpha was 6%, p-value was 8%. We did not reject the null, which is what you show here. Don't reject the null. So when you do two-tailed tests and you get a probability like this one, to put the p-value, you multiply that by 2. Makes 8% to be consistent. So that's all for this video now. And I have more videos coming up later. But right now, this is it.